But every time somebody changes their password, right, and they force you to change your password so often, if your phone is trying to connect to an internet service on there and has a different password, you're creating an error. And so maybe that will affect your account, maybe it won't. It kind of like it doesn't necessarily get transferred over. Right? It could affect more. There you go.
Thank you.
Enough time for class before the snow starts. The next assignment is posted, and that's due on Friday. There are a couple questions on the previous material. Something to deal with power, and then a likelihood ratio type test. So it kind of goes through a few steps to kind of show some of those things. There's a problem on power, where you calculate a cutoff value, and then calculate a probability, like that. And so it helps kind of go through a power calculation. In a likelihood ratio problem, there's a density. It's actually a beta probability density. And it's as if there's one observation. So beta models think between 0 and 1, so your observation could be an estimated proportion. So that might be based on a lot of data, but you just get that proportion, and you just take the ratio. One of these is a 1/2, and one is 1/4. You just put those numbers in there and get a ratio. And so you can rearrange that to get that your data that you have is less than some cutoff value. And below that cutoff value, you would reject. So it kind of helps you through finding that, and then finding a power, a probability. Under the probability density function, if you integrate it from 0 up to a certain point, the solution is just x to the 1/2. That's how it would come out. So that is the probability under that simple model, and that gives you power. If it's a different thing there. And it turns out that in this case, power is not very good. It's only one observation. And then there's some computer code that's given in the R script to help you simulate power under larger sample sizes. Right. And then there's some problems that involve this material we'll talk about today and Wednesday. Largely, we'll be able to talk about a lot of the things we need to do. We'll finish up with more details on Wednesday. So in terms of this homework, a lot of what you can do is, so I'd encourage looking at it, before Wednesday. If you have additional questions on the power and things, Wednesday, Thursday office hours would be good to ask about those. On the R script file that has some things to help with some of these computations for the data, the simulation, and so on. The other thing that we couldn't show the other time under assignments is the projects for this. There's a project file here that talks about different options for those. As I mentioned, there's a lot of different ways that projects can be done. They can be individual, or you can work in groups. You write a project that's about 5 pages. It could be more if there's more graphs and output and things that you want. And then we have some presentations that are about 10 minutes, right? So that we get to see the variety of things that people are doing. And I think that's part of using statistics is communicating it. So it's good to practice doing that. And there's a bunch of different options here. One thing I didn't mention is there's a number of journals or magazines that would be appropriate to read. There's a Chance magazine. I was editor for that for a while. American Statistician is a little bit more math stat. They might have an article explaining and comparing ways of doing confidence intervals or hypothesis tests. Significance of the newer magazine from the American Statistical Association and the Royal Statistical Society, kind of a joint publication. And there's a number of online journals about teaching statistics. So you could look at an article in one of those, rate it, ask me some questions to figure out a little bit more about it, and then write a report about what's in there, what have you learned from it, why is it relevant to the things that you were doing. So there's a number of options. Generally they have an outline of something to organize the comments and what you write up. That's flexible how you do it, but I do recommend kind of thinking about an outline and then a short presentation about that, or data sets. If you do want to do a draft of either the presentation or the project, right, you could send it to me the week before, or at least by that Monday. It's coming up on the presentation's on the Wednesday, and you send it to me on that Monday. I could probably plan some time to look at them and send you a quick feedback to say, well, maybe you want to add one thing on this or clarify this one point or something like that. Okay. So anyway, that's posted, and I think I've figured out my computer problem, so I don't think we'll get interrupted again. So anyway, that's posted there under the assignments for project and presentation in case you want to look in more detail. I do recommend thinking about the project this week, certainly by next week, because there's the Thanksgiving break, and it's good to have it in place so you can work on it before. But any questions? So we are moving on to the chapter on categorical data. Chapter 9 is on linear regression, and that would be a fine chapter to read. It could be the basis of a project, but just in the matter of the time that we have, we're going to focus on this one and then look at some things with Bayesian analysis. Right? The categorical data would be another type of data, and in this case, all our So our random variables that we have record categories. And so the categories can be yes or no, male or female, strongly agree, disagree, strongly disagree. You could do things in kind of a 5 levels or something like that. Race, ethnicity, likely is recorded in a category. Political affiliation, liberal to conservative, something along that line, could be reported in categories. Just the presence or absence of a disease or other condition. So many things can be reported as categories. And if we have 2 variables that are categories, right? We can put the table, we can make a table of counts. Right? And so this will be some table, well, I'll draw it on the next page, right? So that I'll just put it here, right? So that we can have, one variable, so variable 1. And it would have a certain number of categories this way, and variable 2, and a certain number of categories this way. And depending on how many categories you are, you get the cross classification. And every person you talk to or interview or every unit you do a test on gets classified by the levels of variable 1 and the levels of variable 2 and adds to the count that's in there. And across the entire table, it adds up to our total sample size of n individuals. Right? And so just as an example of this, I looked at problem 10.8, and it has many categories in one dimension. And I collapsed it a little bit. So this is children's perception, children's, I guess would be over there, right? Perception of brands and products. Right. This was done in a survey done in rural China, children, and that had seen some advertisements and what they think about these things. They had 1,481 children, right? And some of them are boys and some of them are girls. Right? There were 726 boys and 755 girls. That is up to our 1,481 total there. And they were asked on essentially a 5-point scale what they thought of the products. Did they like it a lot? Did they like it? Did they kind of neutral, didn't care? Dislike or strongly dislike? Right? And so that would be 5 categories. I collapsed those into did they like it or not like it? And this one includes, I included the indifferent to it. So I took the 5 categories and just collapsed it into 2 to make it a smaller table. On Wednesday, we'll look at what would you do when you have the entire table of all those 5 categories. The type of things that we're going to do today could be used there as well. The boys, 440 liked the products and 286 did not. Of the girls, 476 liked the products and 279 did not. This adds up to 916 and 565. And the type of question we want to ask is, are these variables related? Right? Is there essentially a difference between boys and girls in terms of whether they like these products or not? Right? And we could, in this case particularly, do a test using 2 proportions. It's the proportion of liking it among the boys, the same as the girls, and use our 2 sample procedures for testing those. But what we're going to look at are things that go beyond that could be used for all 5 categories, and so we're going to frame it just a little bit differently. But the basic question is, are these variables related? Is there a difference between boys and girls and liking and not liking these products? And so we're going to have hypotheses. Right? And so our hypotheses are going to be that the variables are independent of one another. Another way this might be phrased, which might actually be better for this, because we have the boys and girls, and the boys and girls are not really something that could be changed. That's a physical category of individuals, right? So variables, it might be called proportions of the responses, like versus dislike, are homogeneous or homogeneous. I guess how you could say it, right? So anyway, the proportions are the same across the groups. The calculation we're going to do is going to be the same. The interpretation could be just a little bit different depending on how things are. The other alternative, the alternative is just that they're not independent. Or later in the chapter where it talks about homogeneity of proportions, is that they are proportions are heterogeneous. implication of things of this independence, right? So we are going to have a cell in the table I, J. So it's going to be level I of the first variable and level J of variable 2. Right? And we're going to look at the probability that somebody is in that cell or contributes to the count in that cell. So Pij. So this is going to be the probability that a randomly selected person gives a response I to the first question and a response J to the second question. I'll just kind of abbreviate this. The probability that somebody's in that cell out of all the cross classifications. Right? So we've set things up where we have categorical data and we're putting things into tables. This one has, just 2 levels of this variable, 2 levels of this variable. So this would be gender, and this is an attitude in terms of the names of the variables, and the levels are boys and girls and like and not like. And so there's I could be 1 or 2, J could be 1 or 2. What's the probability you're in one of these cells? Right? Under the null hypothesis that they're independent, well, that you have both I and J is going to be the probability. Oops. It's going to be the probability that you're in I of the first cell, of the first variable, times probability you're in J of the second variable. It becomes multiplicative under independence. And so we're going to compute that probability. How are we going to estimate these separate probabilities? So to do a test or something, we're going to compare the probabilities we have to that probabilities here. So we're going to have to estimate these different probabilities. So sometimes these would be called, here 1, 2, up to I rows, and 1, 2, up to J columns, and say this one here, this little cell here, is for row I and column J. Pij is going to be the probability you're in that cell. Based on all the data, if we have Xij is the count that's in here, right, so we observe here Xij, an estimate of this thing is just going to be, N is the total count, it's just the number that we see in there over there. Right? That's the kind of general estimate of that proportion. But under independence, we're going to estimate it differently. Under independence, we say it's under the first variable, it's that one, right? And so under independence, our just a little I there for independence, our estimate is going to be the product of the estimates of these 2 things. Well, how would we estimate that we're in this row? Right? If you add all the counts over this row, let's say that's the row total. If we add all the counts across this, R1, R2, R sub I, we have the number that are in that row. So to estimate the proportion in that row, we're going to take the number that are in that row versus the sample size. So we're going to have Ri over N, right? Is the first estimate there. And then to estimate the number that are in that column, right, we're just going to add down. So if we add all the counts here, C1, C2, this would be a C sub j, and C sub capital J, the last one. We're going to take the count that's in that row divided by N, and that's going to be our estimate of proportion. Now if the independence model's pretty close to reality. If they really are pretty much same proportion, if it's homogeneous, if it is independence, then this number should be pretty close to this number. Not only in that one cell, but across the entire table. But if there's some departure, like one category, like boys or girls, if they had very different opinions, then it's not gonna match up very well. Right. And so we want some way across the entire table of all those different entries to do a comparison and summarize it together. And to do that, we're going to calculate something called a chi-square statistic. The usual notation is capital X squared for this. And we're going to do a sum over all of the cells in the table of the observed count in a cell minus an expected count in the cell, right? And we're going to square all those and divide by the expected count, kind of standardize them. This is a little j. Where the observed is the actual count that we get there, right, is our actual count that's in that cell. In the cell ij. Right? And the expected is expected under the null hypothesis, expected under the model. And the expected count, abbreviated up there like that, is going to be the number in the sample times the estimated probability under independence. And the estimate under independence is the row probability times the column probability, because under independence you multiply things if they're independent. The chance of them both happening, that row and that column, is the probability of that row times that column. So this was the number in the row over n times the number in the column over n. And obviously you can see that something cancels there. So sometimes the shorthand is just this row total divided by times the column total divided by the sample size. That's because I just want to write it down. So we're going to get the sum over all the rows and columns of the entire table and get this statistic. And if independence is pretty close, deviations aren't going to be too big, right? If sample sizes are pretty big and deviations are small, then this difference might not be, and we're dividing by a big number, so this whole thing's going to be kind of small. So the smaller this is, the closer it is to independence. Right? But if in some place we have a big discrepancy and square it relative to a small expected number, then that gets really big. So the prescription is if down, right. If x squared is too large, then we're going to reject the null hypothesis and conclude not independent. Which means that the row and column variables are associated with one another. Right? But it becomes a question of how do you tell, is it too big? Right? And a lot of our testing and our procedures about testing is under repeated sampling. If you got other samples from this distribution under independence, what would be the extremes? How unusual would it have to be? What would be the upper 95%? If we're beyond the upper 95%, like out in the tail of a distribution, then that's going to be unusual evidence. Right? So, a couple ways. How do you decide? chi-squared value is too large. Well, one way, if the expected counts are all greater than or equal to 10, or maybe all greater than or equal to 5 sometimes is allowed. It's kind of central limit theorem, kind of sample size requirements. There's not a hard cutoff in terms of saying exactly how big they have to be, but the bigger they are, the better. If it's less than 10, the p-values and so on that you would get start to be a little bit less questionable. Then the x squared value, right, under the null hypothesis, right, is distributed as a chi-square random variable with 1 degree of freedom. So this is a chi-square random variable with 1 degree of freedom. That chi-square, this chi-square actually kind of is just sloping down. So under the null hypothesis, we get this. And so under that probability distribution, this 5% tail is here at cutoff at 3.84. So it turns out, if we have a fairly large sample size in the table, and so expected values aren't too small in any of those 4 cells, then our x squared statistic under the null hypothesis should have a distribution like this. And we can say that we reject the null hypothesis at a certain level if it's bigger than 3.84, right? So reject H0. If our x squared value is greater than 3.84. And this is done at the alpha 0.05 significance level. So this approximation, Pearson and Fisher, people at the beginning of modern 19th century, 20th century mathematical statistics, showed that this worked out. And that would be our decision rule. On Wednesday, we'll look at bigger tables that have more than 2 by 2, and then this degrees of freedom will change as the tables get bigger. There'll be more degrees of freedom that we use, but we'll see how to do that. But if sample sizes are smaller, this large sample approximation won't work so well, right? That is, you could get extreme values more or less often, depending on how the table works out, right, with small samples. So the second way to look at this is called a permutation test. So this is not unlike the permutation test that we've done for judging, two samples before, right? So what goes into making our table? Right? If we have 1,481 counts added up in that table, there was a data set that had 1,481 rows, right? One for every person. And every person has boy or girl recorded and like or not like recorded. Right? In the permutation test, we have boy-girl, and we have like versus not like for all of our subjects. And if we tabulate the number of boys and girls, and so each one of these is, 1 or 0 values essentially, 1 for yes, 0 for no. You can code boy-girl 1, 0, 0, 1, depending on how you do. I usually do it alphabetically. So I would put boy as 1 and 0, and girl as 0. If it was male or female male, it would reverse. But so you have to know how they're doing it. But I like to do it alphabetically because that kind of takes the decision out of it. And then like or not like, right? In that. Now under independence, right, if there's no association between these two, it's as if these two values were just plucked out of the distributions for boy and girl and the distributions for like and not like. It just plopped in there. And it wasn't that you took a boy and then took their distribution, and took a girl and took her distribution, but it was just, there's these two variables, just get random values. So the way we're going to do a permutation test is we're going to compute our x squared for our real data, right? That's going to be our data point, right? And then we're going to do random permutations. A way to do that is we're just going to leave the boy and girl column alone. And then we're going to choose a random reordering of like and not like. So if we take all the likes and not likes that we've seen, write them down on little pieces of paper, put them in a hat, mix them up, and pull them out one by time and put them back up there. Right, we randomly permuted the entries. Right? And that should break any association that's there. It should just be random. It's preserved the number of likes and not likes overall, the number of boys and girls overall, but it's breaking any type of associations. Right? Compute x squared, let's call it a star, for the reordered data. How would you have to do that? Well, given the new reordering, you calculate a new table. It's going to have different counts because you've messed everything up. The counts, on average, should be consistent with independence because they're randomly reordered. And so you should get x squared values that are kind of lower, right? The expected value of the chi-squared of 1 is at 1, so it should be on average 1 plus or minus some number, right, with generally low values. Right? And if we do this, permutations, if we do this, a large number of times, say 10,000 times, right? Then we're going to compare our x squared statistic value from the real data to the x star squared distribution, the simulated permutation distribution. And if our x squared is outside, it's kind of big in comparison to these ones that were generated under independence, we'll reject. If our value is in the upper 5% tail or beyond, it's not something you're going to get very often under independence, right? In fact, our p-value is going to be the proportion of our x star square simulated values that are greater than or equal to our actual data x squared. And if that p-value is less than 0.05, so that ours is in the upper tail, then we're going to reject the null hypothesis. So we can either use the exact distribution or that. There's a couple wrinkles we'll go through with a data example. There's one other computational method for testing the same thing. All right, so it's called Fisher's exact test. We'll probably hold off talking about exact computational details of that. This is useful really for the 2x2 table case. It should give you p-values very similar to the simulation value, and most of the time people would just implement Fisher's test rather than program a simulation, but it should be quite similar. So let's look at the data example a little more detail. So one thing you do in the chapter 10 problems is set up a matrix to hold your table of counts. And so the counts in those cells were 440, 286, 476, 279. This thing here puts them together into a little vector, 4 numbers. If I want them in a matrix, I can set them up in a matrix. These are going to be the data for the matrix. And then 2 rows. And I'm going to do it by row equals true. So it's going to do, going to see 4 observations, 2 rows, so it must be 2 by 2. So 480, 440, 286 is going to be in the first row, and 476, 279 in the second one. If this is by row equals false, then it's going to make 440, 286, and then kind of fill it in that way. So you could, if we do that, and then look at the matrix, that's the matrix that's in the book, table of counts, the 2 by 2 counts. You can add dimension names to a matrix, either row names or column names. The dimension names goes as a list, and so the first one is the rows and then the columns. If you do that, you can make it like that, and then it gives you the things that are labeled. We might want to calculate the row totals, right? So whenever you have a table of counts like that, consider adding across the rows, adding down the columns. There's a command in R called apply that will apply some operation to the rows or the columns of a matrix. Right? So here's the 2 versions of that. The matrix is the input, 2 by 2 matrix. 1 means preserve the first row, first dimension. Right? Preserve boys and girls in this case. And then sum, add, the counts across there. Right? So if you do that, you get those two counts. So there's the counts. It preserves the variable names, the dimension names, which is kind of nice. So 440 plus 286 is 726, and that's that first one there. And this one plus this one is the 755. The second one, we preserve the second dimension. Right, you add down this way, so you get 916 here, and a smaller number, don't like that. If you add up the total of the matrix, you get the 1481 respondents to the survey that made that sign up. So once we have these, if you had to estimate the proportions in each category, just based on the data, you're going to take each of these numbers, just divide by 1481. And that's just the observed proportions that are in each of those categories. It's not under any model, that's just the data. And so if you divide just the matrix by, here, that's this one, the matrix divided by 1481. So about 30% of the respondents were boys who liked the product or thing they were asking about. 19.3% were boys who did not like it. 32% were girls, 18.8% were girls who did not like it, right? So each one of these percentages is simultaneously defined by 2 variables, levels of 2 variables. But we can calculate the proportions of boys and girls, right? How many boys and girls were there? Right, those are the boys and girls. And if we divide that by 1481, we get the proportions, right? Divide each of those numbers by that. And same thing for like or not like. So we're going to get those numbers, right? So if you put that numbers for this example into a table, right? So there's boys and girls, and then like, not like. Those things on the columns, on the sides, let's see, did I write those things down? Oh yeah, so there was 49% were boys, 51% were girls. And in this column, 0.6185 did not like it, or liked it, and 0.3815 did not like it. And both of those, whether you add up this way or this way, add up to 1. Now if things are independent, we can figure out the proportions that would be estimated to be in here. So for this one, we take 0.49 times the 0.6185. Multiply those two things together, and it's 0.3031. Where did that come from? 0.49 times 0.6185 ends up being this 0.3031. So under independence, we would expect 30.3% of the respondents to end up in that cell. What is it actually? In the actual data, it was about 29.7%. It's a little bit less. So if you just take the matrix, itself, divided by 1481, there's 0.297 that's there. We expected under independence it to be a little bit higher. It's not very far away. To me, it doesn't seem too far away. Under independence, we'd expect 30, and we actually got that. This one, the actual data is 19.3, and we would expect, by multiplying together, 0.18. So it's not a whole lot difference in this case. So these other ones, this is 0.51. So this one, okay, went up here. If we take this one times this, it's 0.3154. These two still add to that row. But that number, take 0.51, 51% girls, times 61.85% in that column, gives us the 0.3154. And so this one, right, goes into that number. If you take the 3815 times this number, you get 0.1946, and this number times that one is 0.1870. And the actual numbers are a little bit different from that. So that's comparing the proportion. Now to get the expected numbers, we would multiply both of these things by our 1481. Right. So if we do that, we have a table that, so our original data table had 440, 476, 286, 279 over here. Our expected table under independence, if we take the proportion times the, it's going to be 448.8. You don't have to round to an integer for expected values. They can be decimals. It's best to keep them as decimals to some degree of accuracy. 276.9 and 467.2 and 288.2.
That's different than on this sheet.
It is different from on the sheet. Do I have it backwards?
On the sheet it says the first one's 0.449.03.
Oh, okay, yeah. So what's happening is on the sheet, I actually kept all the decimal places. And this has a little bit of rounding problems. Right? But 276.9. So yeah, it would be a little bit higher, this one's a little bit lower, and so on. A little bit higher, a little bit lower. So rounding, as I did it there, kind of threw it off. See the sheet for more accuracy. Okay. So we have to calculate those things. So what Gavin is mentioning is that on the sheet, right, there's a way to use matrix calculations to do these things a little bit better. This little thing means matrix multiplication in R. Like in Maple, if you use Maple, you can do these things, and R has its companion too. We don't do too much of it in this class. If you take Statistics 351, which is next fall, that does linear regression, it does much more with matrices, because the natural way to express linear regression is with matrices. So you end up doing more with matrices. So these are the proportions in there under independence. This is actually, this thing here is the proportions of boys and girls expressed as a, like that. Where'd that rest of that go? The rest of this part here, this one here is set up to be a column. So the proportion of like and don't like. And what this does is multiply a matrix that's 2 by 1 versus 1 by 2. So it actually gets a 2 by 2 matrix, or 2 by 2 table. So if you've had linear algebra, done things with matrices, that's what it's implementing. And the result of that calculation ends up being the expected values. A little more accuracy than I did by hand at first. So these are our expected. Those are our observed. And do they look similar? Does it look like there's much error? We know that there's going to be some random variation just by chance, even if they are independent. So at first pass, that doesn't look too discrepant. Not obviously, really bad. So to do the chi-square calculation, it's convenient to save the observed data. You can just call it mat for matrix. All right, O. Now O is just my matrix here. My expected values I'm saving as E. Right? Oops. I just put E here. Right? Those are my expected values. And what I do is I compare observed to expected and standardize, so square them and divide by the expected counts that are there. Right? So if you have a table that has counts that are, say, in the thousands, a discrepancy of 1 or 10 or something is not so big. But if you have a table that only has counts of 20, a discrepancy of 10 is enormous. So relative to the size of the bigger tables, bigger counts, you expect more absolute differences. The percent differences might be smaller. And so the chi-square contributions are these pieces. Right? They're all quite small. These things can be bigger than 1. And if things are not independent, they would be bigger than 1. But we add them all up, and we get a chi-square value of 0.934. Okay. So in this particular example, for judging are they independent or not, these data here produce x squared equals 0.934. And we have to decide, is that a large value if they're independent? If they really truly were independent. And so one way is to look at the chi-square distribution. Here's a picture of the chi-square distribution, or at least part of it. Make this bigger. The chi-square is kind of funny with 1 degree of freedom. It's just kind of sloping up, right? But there is an area of 1 under this. It just kind of gets really big there. It's kind of hard to see. Not the easiest, not the greatest thing. This is the cutoff point. If you're out past 3.84, we're going to decide that it's not independent. Here's our actual one in blue. We're actually back here. These are just some lines you kind of put into 0 points. So we can kind of see the area under it a little bit better. Just kind of jumped around. The probability of this little tail area, it's hard to picture, but it's.
You went down.
I went down too far. Let's go back up here.
You need to.
Let's see what's going on. Let's go back page down. The chance we're bigger than that 0.934 with 1 degree of freedom is 0.33. So it's kind of hard to see from the graph because it's just so funny. But about a third of the probability is actually out past there. So our p-value is going to be this 0.33, which is much bigger than 0.05. And so independence, we're not going to reject independence in this case. So don't exactly match the independence counts, the expected counts, but they're not very much different. They're pretty close, given that. So that's whether you look at the p-value and say, oh, it's not bigger than it's bigger than 0.05, don't reject, or you look at the statistic. Our statistic was 0.93, and the cutoff is 3.84. We're not out far enough. We have to be out here to reject. So yeah, so that they don't seem to have a different distributions, boys and girls. In the survey in rural China, looking at the impacts of advertising and branding, don't seem to have a different opinion about the rate of liking or disliking things. Maybe they like and dislike different products, but the overall rates do not appear different. Now, there's a chi-square test in R that will do these calculations for you. On the homework, I suggest you look at the formulas, on the test, where we would evaluate this. And I'll give you a 2x2 table, and I'd ask you what are the expected counts. So calculate the row total, the column total, and figure out what the estimated, the expected value would be under independent. So being able to use the formula is important. You can check it. The chi-square test here gives a chi-square statistic. Degrees of freedom 1, because it's a 2x2 table. The input is our matrix. Right? Our 2x2 matrix goes in there. This thing will calculate row totals, column totals, expected values, and the statistic, and it gives a p-value of 0.33. Because this is discrete, because it counts, and the chi-square is a continuous distribution, there is a continuity correction. Just like you went from binomial to normal, there's a little continuity correction. And so it's either adding half to some counts or subtracting half. And if you do it with what's called Frank Yates continuity correction, it adjusts the statistic a little bit, and the p-value is adjusted a little bit. If you were closer, if a smaller table that was closer to about 10 expected values in there, the continuity correction is kind of recommended. Otherwise, it shouldn't make much difference in the conclusion. You can also simulate p-values, which is like our permutation test. So how would you know that stuff's there? Help, chi-square.test. Pearson's chi-square. Simulate p-values is an option there. Where does this come from? There's some examples there, but I didn't give the original Pearson reference, but a couple of other things. There's a journal called Applied Statistics, so there's probably an algorithm in Fortran that's behind all this that does it quickly for large tables. So anyway. So if you simulate it, it will simulate the p-value. You can tell it how many times to simulate. The default is 2,000, but you can make it 2,000 if you like. And if you run this, it is generating new tables with the fixed margins. It's doing something like our permutation. Our chi-square statistic is this. It's not dealing with degrees of freedom because it's simulated. And it gets a p-value that's very much the same. If we run that again, we'd probably get a slightly different answer, right? Because we could get, so it changes a little bit based on simulation, right? These p-values are changing just a little bit because we're simulating 10,000 tables and not always the same. We will talk about what goes on with the Fisher exact test. Fisher test is built in. Fisher test basically says if you have 2x2 margins, there's only so many tables that can fill that out. Right? And once you put in a certain count in one of those, and they have to add to the margins, that's the table. And then under a hypergeometric distribution, a certain probability distribution, you get the probability of every table. So of all the possible tables you can get, how unusual is the one you actually got? So it actually calculates probabilities. It's so-called Fisher's exact test, and it gives a p-value too. Very much similar to the simulation one. So basically everything's consistent in this case. These things look reasonably close to independent. Something else that this chi-square test does, so the names chi-square.test out that, is there's a number of things that get calculated and are stored there in that object. And what you see by the default is its default way of printing it so that you can see what generally people want. But that other stuff is there, right? It has the observed matrix. It has the expected counts. It has some residuals, which are differences versus that. So if you do the expected counts, you get the expected values. Right? And this was what we calculated as little e, right? Those same numbers that we calculated. So you can use that chi-square test to get the expected values, but on the assignment I do encourage you to practice doing that, but you can check it, seeing if it's working out there for you. To set up a permutation test like we talked about, right, setting up this permutation test. Oops. Well, no, maybe it was after that, right? Oh, no, it was before it somewhere. this permutation test, right? To set this thing up, right? The only way I can think about doing it is actually having a little table, right? And so in many cases, you would do your surveys and enter something for everybody. So you'd have something more with of this kind. You wouldn't have a 2x table. You would have all the data. And probably you don't just ask these individuals 2 questions. You probably ask them a whole bunch of questions. And these two are 2 particular things that are there. How can you program it to work out? Well, let's set up a variable called boys and girls. This little rep or repetition is a convenient way of working in R. So it's going to repeat boys 726 times and girls 755 times. Big long vector there. Right? And I'm going to set up another variable called like. Right? It's either going to be like, not like, or like and not like. And it's going to repeat the number of times that happens in the table. So among the boys, there's 440 likes and 286 not likes. Right? And then among the girls, there's that number. So if you set those 2 things up, you get new variables. So this environment up here, you have the BG for boys, girls, like, just like or not like. The table of that boys and girls. I don't know why it gives me those other things. But the first 10 values of boys are all boys. And then eventually some girls come into the list there. Table for like, like the first 10 values of like are all like because there's a whole bunch of those. Eventually there'd be not like, and then it's going to repeat. If you table those, it matches our data. And if you did a chi-square test of this table of these 2 variables, it will, oops, it's highlighted still, it will give us our chi-square statistic. Right? So we said with the permutation, we calculate the statistic for our data. Then we go through a process of permuting data. We do 1,000 times, 10,000 times. We're going to calculate the statistics for permutations. N is 1481, and we're going to randomly mix up this column of likes, right? And a permutation can be implemented like this. So we're going to sample the numbers 1 through n, so 1 through our sample size, as many times as our sample, and with replacement equals false. So we're going to take all the numbers and just pick them until they run out. But in the end, they're going to be in a random order. Right? And so like of that new order is the like one just randomly permuted. So that works there to do that. And then we're going to do the chi-square test and save the statistic value. The book talks about writing a function to compute that. You can write your own little functions in R to do computations you're going to do over and over again. So it does a little bit of that, but you can take it just from this thing. If you run that, here's a histogram. Here's the histogram of the simulated values. Not too unlike that really skewed chi-square 1 distribution. These are the simulated values. Here's our actual statistic. Does it look unusual? Compared to these random permutations under independence, our actual value is pretty much in the middle of those. Right? Not exactly the 50% point, but in the middle. Here is the 95th percentile of the actual permutations. When I did it before, I got 4.12. This time I got 3.72, so it's pretty close to that 3.84. It seems to hold up pretty good. We have pretty big sample sizes, so that chi-square 1 distribution should be a pretty good approximation to that histogram. But in either case, it's not unusual. Let's look at one other. Right. So anyway, the conclusion would be that there does not appear to be much of a difference, right, between these. It looks pretty independent. Now, that's a pretty big table, right? Let's imagine we had a smaller sample size, kind of a pilot study. So let's say we had boys and girls, and we had 73 boys, say, and 76 girls. That's about the 10th of a size of those. So that's 149, about a 10th of the size of the original survey, right? And then like and not like. And say that we had 44 and 29 here, and 48 and 28 here. If you go through all that calculation, if these are the data, the expected values would be something like 45.07 and 46.93 and 27.93 and 29.07. And then the chi-square statistic we would calculate from comparing these observed and these expected also is quite small. Do not reject independence. So if I take about a tenth of the size of the original table and shrink it down, it turns out to not reject either. But I'm shrinking this down to now show you a different table. Right? So if you follow through, you could check. We could check 80, this is 92, 92, that's 92, 92, and this is 50, 57. The expected value, for instance, is the first cell, first row. We have 92 here times the 73 over the 149. That should give you this 45 number, for example. And you could check different ones just to make sure it's clear. What if, however, the table didn't look like this, but instead we had a table that, boys and girls, like, not like, was 34, 39 for our 73, and then 58, 18, 76, our 149. This still adds up to 92. This still adds up to 57. How about that table? Hypothetically, say we're asking a question, and there's like, not like, and boys and girls, and it turns out like this.
And 18 is too low.
18 is quite low, right? This is going to have the same expected values as the other one, right? Because the margins are the same.
39.
Yeah, so this is 45.07 again, 27.93, 46.93, 29.07 are the same expected as that previous table, right? Because the margins are the same. And under independence, if the margins are the same, you get the expectation. But this one does not look like that one, right? The differences are quite large, and if you do the x squared value, you get 13.94. Right? We still compare it to a chi-square. One, the 95th percentile is 3.84. And so this one, if this were our data, we would clearly reject the idea of independence. Right? So a little bit more involved statistic for that. A lot of the same logic as hypothesis testing. A few different ways of going about the test to get p-values, to assess significance. And we'll come back on Wednesday and look at doing this with bigger tables, 3 by 3, 5 by 6, or other things like that. Yeah, just calling it.
So, I don't know, I thought.
And so it wouldn't really in here, portion, there's one